Okay, we were talking about some of these digital circuit blocks and gates, and in general, we said that we can make an inverter by simply doing a circuit like this. So in this circuit, if the signal Vin is 0, if this Vin is 0, if this is 0, output, if this is 0, the transistor is off, and then no current flow is here. So V out is going to be VCC or VDD. Okay. If it is BJT, typically we call it VCC because this is collector, emitter, and base. So voltage drop is low, so that we have here an output. So we call this thing VCC, but the highest value of that is called V output high, the highest value of output. And then, we'll be seeing the operation principle later on, but this point, which is 0.7 volts, after which the transistor starts conducting, we call this thing V input low. And then here, the point where it goes to saturation is called V input high point. And then this point where it corresponds to V output high, this is called V output low. Okay. So therefore, if the input is here, input, let's say this is the input low, input low will result in output high. Output high signal. Okay, so therefore it's an inverter. So if the input is high, okay, maybe I should use a different color. Okay. Input high. This is going to be output low. Okay, so therefore it's going to be an inverter. So when we have high input or low input, output will be high. Okay. And then when we have high input, output is going to be low. So that's going to be logic. So in general, the response of an inverter is like this. So we call this thing voltage transfer curve or characteristic. Okay, and we, when we look at this, we said that this is as a definition is called V input low. This is as a definition V input high, and this is as definition V output high. This is as definition V output low. Okay, so maybe I should use different colors here. And then, do this here. We output low, and this one, we should call this thing V output high. So, so apparently, since we are going to be, connecting output of one of them to the second one. So when, let's say, this signal is let's say 0. Okay, so, or the other way around. Let's say this is high. High signal is applied. And if high signal is applied, output is going to be the output low. And for the next signal, this should be below the input low. Okay, so the output at this node is going to be the output low. It should be lower than this one. So if we apply here, this is going to be the output low, and it should be less than this one. So that output of the next one is going to be the output high. And that the output high should be larger than the input high. So that the output high should be larger than this one. So that proper operation is going to be happening here. Okay. So this difference is important. The larger is better. And as we defined, we call this thing, I guess, noise margins. Maybe I can define it here also. The noise margin low means, as definition, the distance here. So this is the noise margin low. So the input low minus the output low. Okay, so this is called noise margin low. And this distance is the noise margin high. And the noise margin high, as definition, is the output high minus the input high. So, you know, for proper operation of the signals, if this is logic 1, this is going to be 0, this is going to be 1, this is going to be 0. You know, to get the proper signal flow, these are important. Larger is better. And here is also the larger is better. Okay. And both of them should be larger. I mean, if one of them is 5 volt, the other one is 0, it's not no good. Okay. For an ideal case, as you know, for an ideal inverter, remember, you know, ideal inverter was like this. So this was VCC divided by 2, and this was VCC. And therefore, here for an ideal inverter, the noise margin low is 2.5 volts, like VCC divided by 2 minus 0. And the noise margin high is VCC minus VCC divided by 2. That is, again, 2.5 volts. So if there is any noise here in the signal at the output, still it's going to be considered as low. So that's the point here. Okay, so another way of showing this is like that. So this inverter, we don't know what is inside. So, but it's going to have, let's say, it's going to have an output. Okay, so when this says my output is the output high, okay, it should be larger than for this inverter's input, okay, the we input high. So the difference is important, and this difference is going to be called V noise margin high. Okay, so here the output here, okay, output of inverter A, and this is input of inverter B. Okay, so when this one says that I'm giving you low output, V output low, it should be less than this value. And then how much less? The voltage here, the difference, we call it noise margin low. Okay. So the point here is, this is input low. Input low should be larger than, or output low should be lower than input low. So that is the basic idea here, because if it is the other way around, then it won't work. I mean, it won't work. When they say that I'm giving you high voltage, this is not accepting as a high, so therefore it will really not work. So as definition, noise margin high is defined as V output high minus V input high. Noise margin low is defined as V input low minus V output low. So if this is the other way around, for example, if this signal, let's say the output high is, let's say 3 volts, this one is the output low is equal to 2 volts, and let's say this is the input high, 4 volts, and then this one input low is 1 volt, then this won't work. Okay, this will be really bad. It won't work. So that's the definition. So for the circuit topologies, I mean, you have seen it here. You have seen it here in one example. This was for this circuit. This was 0.2 volt. So here, noise margin low was 0.7 minus 0.2 volt. Not good, you know, only 0.5 volts. The other one, we don't know. I mean, this is maybe 5 volts. So we can design this to be maybe 2 volts. Then there's going to be huge noise margin, but it's unnecessary. So we can do some additional, you know, things to the circuit to shift this, the input low, to get a better noise margin. Okay, so maybe we can put here a diode, and then the noise margin, if you put a diode with diode, additional diode, then the input low becomes 1.4 volt. Therefore, noise margin low becomes 1.4 volts minus 0.2 volts, which is 1.2 volts, which is better. Okay, so this is just in parentheses maybe what we can do. Okay, with the help of a diode. So we'll be seeing some circuits and then check this condition and calculate noise margin high and low, I guess soon. So these are just the definitions right now. So another critical thing here is the what is the fan in and fan out definitions. Okay, so here for the logic circuits, this is what? This is NAND. This is 3 inputs. 3 inputs, NAND gates. Okay. NAND, why? Because of this negation is coming. And circuit. So for these circuits, we need to connect them to other gates. Remember, we were calling these as gates. Okay. So gate. Or maybe I should put it here. NAND gate. Okay. So, you know, how many we can connect is called fan out. Okay. So here the loading is going to be the fan out of the circuit. Okay. So here the fan out for this circuit is equal to 3. Why? Because there are 3 of them connected here. What about fan in? Fan in is this one. Fan in is also 3. It happens to be 3 here. Okay. So, you know, for these gates, we need to find how many we can connect at the output and still the
Hocam,
circuit properly works. Yes.
alttaki NAND gate'te de bir tane input yok mu? 4 olmayacak
That's
yani.
another one. Maybe it's coming from another circuit. Okay, so it's coming from another gate. So this is why we call this thing 3. I mean, for this one, it is 3. Is that okay?
Okay.
You know, because in the logic circuit, you know, there will be some other circuitry providing the input to here, because that's going to be logic gate. So that's how it's counted. So, I mean, for this one, fan out is equal to 1 because it's only connected to 1, for example. Okay. So for us, it's important for us to determine maximum fan out, because if we connect more than what this gate can drive, it's going to be a problem. Okay, if it is less than that, that's no problem. I mean, we can say that this NAND gate can drive 10 gates, 10 gate inputs. But then if we connect 1, that's no problem. But if we connect 11, it won't satisfy this noise margins, for example. It won't satisfy the operation. Okay. So, how many we can connect, and we can still have proper operation. Okay, let me turn on the music, turn off the music. Sorry. Okay, so why do we have some limits? I mean, what is limiting? Why cannot we connect, let's say, 100 gates at the output? Typically, when we connect, a gate, like in this one, okay, maybe I can start explaining from this one. Like this one, okay? For this gate to operate properly, it needs current. Okay, it needs current so that transistor can saturate and the output can reach to 0.2 volt. Okay, so therefore, we can say that here, maybe I can draw it just for fun. For this circuit, I mean, this is one of the circuits that we see. There will be other circuits. Okay, V in, V out. This circuit requires current. Okay, so this one for I input high, so that means when we connect here, let's say 5 volts, there's going to be a current. So that current should be enough so that it can drive this and then output can reach to 0.2 volts. So transistor can saturate. Okay, so that's the basic idea here. So this one, however, when it starts giving the current, it cannot provide that much current. So this one, for this one, the current that we talk about is going to be for input high, or for the high case here, it's going to be input high. And we typically, for the next gates, we call it input high prime, but that's okay. When this node is high, we call this thing input high. And then here, if the voltage here is low voltage, then we call this thing, we input low voltage or current. So, in the circuit, maybe I should draw it here. For each circuit, there is a current. Let's call it I input high. That means the current necessary for proper operation. Okay. So that current is necessary. But for the circuits here, the gate is going to be giving current, and that current that is given is called, let's say, let's make this color maybe differently. I output high. So the output current is maximum it can give. It can provide, maximum it can provide. It doesn't have to provide. The maximum it can provide. Okay. It can provide and still operates properly. Okay, so these, what does operates properly mean is going to be coming maybe later on. Okay, we'll be talking about those later on. So this is the necessary one. This is it can. Okay, so for the high case, let's say at the output node, that values, those values as definition give you the maximum fan out. So for output high case, we will be finding a maximum fan out, how many we can connect at the output. Similarly, for the low cases, so if this is low voltage, then you know, the current directions I'm writing it, you know, right now conveniently. So this can sink, maximum it can sink is going to be this current. So we can call this thing as I output low, maximum it can sink and still operates properly. But then for this one, we will call this thing V input low. But V input low is necessary. The current necessary for proper operation. Okay. So, and that will be defining another limit. So for output high case, we can find that, okay, we can connect 100 gates at the output. And for the low case, we can find out that we can connect only 10. So what is the maximum we can connect? I mean, considering that this voltage keep changing between high and low, in both cases, it should be satisfied. Therefore, we determine the maximum fan out as the minimum of these maximums. Minimum of this, and minimum of those two is going to be N max. Okay, so maximum fan out, how many we can connect at the output is going to be determined from here. Okay, are you with me? Okay, so This should be integer. Okay.
Hocam sesim geliyor mu?
Yes.
Hocam şimdi şeyi soracaktım. Biz burada en kadar yeni inverter bağladığımız zaman şimdi current bölündüğü için azalacak. High'ken low'a düşebilir diyoruz herhalde. Bu yüzden de beklediğimiz yani aynı şeyde operate edemeyecek diyoruz değil mi? High için düşündüğümüz zaman.
Yes, that's the basic idea. I don't know if I have an example here. I guess it looks like there's an example. So the example, I can solve you an example. Okay, let me do that. So let's say that we have a gate. Okay, and for this gate, I output high is given as minus 4.2 milliamp. Wow, what does that mean? Maybe I shouldn't go to that right now. This is, no, we shouldn't talk about minuses right now. It's too early. Okay, let me go step by step. Okay, so we can say that the current that this can give, output high, is 4.2 milliamp. And this is maybe the same inverter, similar type inverter, I would say. But this inverter needs a current. And I input high of this inverter is 1 milliamp. Okay, so this is a necessity for proper operation. This is required. Okay, so if I connect 1 here, what is going to be the current here? What is this current?
1.
Yes, it's going to be 1 because this is necessary for this one to operate properly. Okay, so Ix is going to be 1 if you connect 1 here. So if I connect 2, what is Ix here? 2 milliamp. Yes. Okay. So so what is N high? Considering this value and this value, we can find it by doing this. I output high divided by I input high, which is going to be 4.2. It should be integer. So N high maximum is 4. Okay. Is that okay? So for the high case, when the output is high here, that is the maximum.
Hocam,
Yes.
burada input high 1 miliamper dediğimiz şey minimum değeri değil mi? Yani input high'ımız yani 2 amper olsa 2 amperlik inverter'a 2 amperlik input high gelse 2 miliamperlik pardon. Yine properly çalışmayacak mı benim inverter'ım?
Say it again. Sorry, I missed it.
Şimdi input high'a 1 miliamper demişiz ama bu minimum değeri mi maksimum değeri mi? Onu anlamaya çalıştım sadece.
That is the, it's kind of fixed. I mean, it's kind of fixed. The maximum value, I would say.
Anladım. Peki hocam şimdi iki tane bağladığımız zaman benim output high'ım 4.2 miliamperse kalan 2.2 miliamper nereye gidiyor?
No, this is, it can give. It can give for proper operation. Let's say, you know, we remember we have this device, right? So when we had the out inputs, I mean, when we see the circuits, I guess it's going to be much clearer, like this one, right? I mean, we say that this transistor is off, right? That's the case for output high case, right? So this is off, and the output is VCC. So the RC, what is this voltage?
VCC.
VCC, right? So let's say VCC 5 volt. My voltage is 5 volt. And then this is connected to the next gate. And the next gate is going to be like this, right? And then this is going to be in saturation. So that output is going to be 0.2 volts. So this is going to be 5 initially. Correct?
Evet.
So there's going to be a current needed here. So if nothing is connected here, this can give a lot of current, but it is not giving any current. So it's okay. But we will find the limits, you know, how much this can give, because if this gives current, you know, output current, then the voltage starts dropping here. It's not going to be anymore 5 volts. It's going to be maybe 4 volt. Is 4 volt good enough for the next gates to be accepted as high? It depends on our value here. So if we apply 4 volt, it is going to be still larger than this input high. It's okay, right? If this input high is 3 volts, then we cannot put more so that this starts dropping. The noise margin becomes 0, for example, or even less. Therefore, I mean, we will be seeing these in real circuits later on. These are just definitions, but the important point here is this is maximum it can give. This is necessary for proper operation. Okay?
Anladım hocam.
Okay. So when you connect nothing, it gives 0. If you connect 1, it will give 1 milliamp. If you connect 2 milliamp. IX is going to be 2 milliamp, okay? So let's do this for the other case. The other case is, let's say, this case. Now maybe I should do it another color again. Now this time, we will be defining output low. I output low. It's given as 6.9 milliamp. And then here you have input low. Input low is given as, again, let's say 1 milliamp. It doesn't have to be. Okay. And then when you connect here, what is the current here? I X low. Let's call this thing IX high. If you have one of them, that's going to be 1, right? So if you connect 1, if you connect 2 or 3, this is going to be 3 milliamp. Okay. So what is the N low maximum?
6.
Yes, it will be 6. So how do we find it? We first divide V output low to V input low, and that's going to be 6.9. Therefore, it's going to be NL max is going to be 6. Okay, so I mean, what happens if you put 7? Is this going to be burning? No, but noise margins will be affected, and then you know, your circuit maybe is going to operate at room temperature, but manufacturer says I cannot guarantee this to be operating every temperatures, for example. Okay, so that's kind of the idea. And in the exams, you know, we want you to show you this, for example, as 6. Okay, here it's going to be 4.
Hocam,
Okay. Yes.
şimdi 6 tane bağlamadık, 4 tane bağladık dersek yine sıkıntı olmayacak mı? Birinci inverter için.
Of course. Therefore, this is noise margin high max. This is noise margin low max. Therefore, let me do it maybe with different color again. So it will be easier to follow. From here and here, we will take the maximum of it. And then we say that maximum fan out, N max. What is N max?
6.
No.
4.
4. Minimum. Minimum of these two.
İşte hocam şimdi 4 kullandığımız zaman o zaman low için sıkıntı olmayacak mı? 4 kullandığımız zaman 4000 amper gidecek. Bu da birinci inverter'ın properly çalışmasına engel olabilecek bir durum olmayacak mı?
No, no, no. 4 is good for this one. And 4 is good for this one also. I mean, this is the maximum 6. So 4 is less than 6, right?
Anladım. Anladım.
Okay.
Evet, okey hocam.
Okay. Okay. So these are the you know, for every circuit that we will be making, then we will be comparing first these noise margins, right? So if these are okay, like output high is larger than input high or not. And another thing is to look at these currents, you know, current wise, if they are compatible, and then maximum fan out. Okay, so one extra thing that maybe I can mention here, or I can mention later on, is the direction of the current. If you look at the data sheets, in the data sheets, the currents are defined according to, maybe I should draw it here. There's already here, maximum fan in and fan out. The currents are defined towards here, towards the system. So I input high, and then I input low, I output high, I output low. Okay, so if you look at, for example, this value, I told you that output high is 4.2, right? But in the textbook or in the data sheet, this value, I output high, is given without defining the direction, because we know that direction is towards this device. So in the data sheets, I output high is given as minus 4.2, okay? And maybe I should do that with different color. just as a note, in data sheets, I output high is given as minus 4.2 milliamp. Okay, and then I input high is correct direction, 1 milliamp. I output low is correct direction, 6.9 milliamp. But here, for simplicity, I gave it like plus, but I input low is given as in the data sheet, if you look at it, 1 milliamp. Okay, so this is data sheet definition. Okay, now that you just learned this subject, and then I'm confusing you a little bit, sorry for that, but okay. I mean, here for the simplicity and the way convenience, I explain this way. But then, that's what you will be seeing in the data sheet. Okay, convention is.
Hocam, can you show us the diagram that you drew just before writing this? Okay, thank you, hocam.
Sure. Okay, so sorry, I couldn't fit it into the same place. Okay. So we will be seeing some different circuits, and for these circuits, we'll be determining all these. Again, that's going to be your exam question, for example, or homeworks. So what is the maximum fan out of this circuit? Okay, you need to calculate that current, those currents, input low, input high, and we'll teach you how you will be calculating them. Okay, another definition. Is that okay up to now?
Hocam bir sorun vardı burada.
Sure.
Yukarıdaki enel max'ı hesaplarken negatif bir değer çıkıyor. Yazdığınız
No,
değerlere
no.
göre. Yani 6.9 bölü eksi 1 miliamper dediniz ya. Direction.
Yeah. But you have to, when you do this properly, then you have to put, one of these as minus.
Tamam.
I mean, okay.
Akım direction'ından dolayı. Tamam. Tamam hocam.
Okay.
Teşekkür ederim.
Or Haluk Hoca define it in absolute value, for example, here. Okay.
Teşekkür.
Sure. Maybe I should put here, those. Okay. Just to be correct here. Okay. Now, another thing is we will be looking at these inverters. Timing is also critical. Delays. Okay. So, the input is here, and there's going to be out. So we will be switching the input voltage from high to low. So maybe 0 volt to 5 volt. So or 5 volt to 0 volt. When you switch this signal from high to low, we expect the output to be switching from low to high. Okay, but there's going to be a delay. I mean, because there are capacitances inside, and then you need to charge those, so it cannot happen instantaneously. So the output is going to go from output low to output high. So this output high might be 5 volt or 4 volt, whatever. Output low can be 0 volt or 0.2 volt or maybe 1 volt. Okay. So this transition is going to be have to be calculated. So typically we calculate this by considering 10% point and 90% point. So this is called 10% point, and this is called 90% point. And the difference between 10% for the signal to reach between 10% to 90% is called rise time. Okay, so what is 10%? 10% is the 10% of the swing. Okay, so therefore this voltage, if you want to calculate this voltage, that voltage is equal to the output low plus 10% of 0.1 of how much? V output high minus V output low. Is that clear? %10 of the voltage swing, output swing. Okay. And how about this value? This value is going to be either you calculate from output low or you can calculate from the output high. It's going to be the output high minus 10% of the output high minus the output low. That's 90%.
Hocam bir soru sorabilir miyim?
Sure.
Bu %10 ve %90 belirlenirken acaba voltajların sabit olmamasından dolayı o dalgalanmaların göz önüne alarak mı bu belirlenmiş acaba? Onu merak ettim. Neye göre yani %10, %90'dan gidiyoruz?
The definition is saying that, like, 10% of the swing is not that critical. It doesn't change the output at all. So therefore, for the next gate, that's not very critical. So it is just a definition. I mean, 10% to 90%. So signal seems still at 90% seems to be high. At 10% seems to be low. So that's good enough. So they have to make a definition. That's how they make it. Engineering approximation, like 10% high, 10% low is not that critical. So let's define it accordingly.
Sağ olun hocam.
Okay, sure. So as you can guess, here we also have 10% concept here. 90% to 10% of the swing is called T fall time. Okay. So of course, the smaller is better for us. Why? Because then we can operate this and then make this switching much faster. So let's say this is going to be a clock signal. Okay, so if this is the period T, okay, so this is maybe going to be T divided by 2 and T divided by 2, right? So T determines F. F is 1 over T. Frequency of operation can be, much faster with this. So what is the maximum frequency of operation? You know, you can look at the rise time. At least it should be like rise time, and then it should be lower than the fall time. And then you can determine maximum operation frequency. Okay, smaller is better. It's clear. Is that right? Okay. But the point here is the output of this is going to go to another inverter. So this output is going to be input for the next inverter. But the input to the next inverter is not so sharp. So we cannot really use this definition now, 10% to 90% definition, okay? So if the signal is coming here from another similar inverter, okay? So input of this gate is like this, and the output is going to be like this, okay? So therefore, we cannot really, you know, look at the signal like this. So 10% to 90% maybe is not going to be very useful for this kind of case. So for these kind of cases, then we look at the 50% points. Okay, so 50% point is this one. And for this one, the 50% point is this point. Okay, so this is 50% point. And this is also 50% point. So when you switch a signal from one case to another case, then there's going to be a delay between these two. And this signal is going to be something of interest. We call this thing, and then we look at from this rise point, propagation delay from low to high. That's how we define that, okay? 50% change. So because the output is going to be changing high to low, low to high. Okay, so the midpoints, let's look at it, how much delay there is when this is switching. And as you might guess, I mean, the 50% point is this voltage. So we output high plus we output low divided by 2 is this 50% point. Okay. So similarly here, there is 50% and 50% points. So maybe this one. Okay, this delay is going to be called T propagation high to low. Okay, so once you find out those, you can either find the average propagation delay, or you have to consider the worst case operation. Worst case means, you know, this is the longer one is the worst case. You know, you can either calculate P propagation average as T propagation low to high, T propagation high to low divided by 2. But, you know, sometimes in order to determine F max, you have to take the maximum of T propagation low to high, T propagation high to low. Okay. Sorry, maybe 1 hour. This one is going to be, maybe I should try here. This one, okay, let me write this. times 2, 1 over of this is going to be your F max, maximum operation frequency. If you consider 50%, I mean, if you consider the clock frequency to be like this, okay? So this is going to be 1 over F. Is it okay? Oh, we
Hocam
forgot.
bir şey
Yes.
sorabilir miyim?
Hı hı.
Bu mesela spesifik cihazların frekansları belirlenirken baud rate'lerin sınırlamaları falan buna göre mi belirleniyor?
Yes, of course, you know, because the circuits don't operate properly if you do operate it faster. So therefore, you should do this. I mean, you should consider these, you know, but you know, maybe some part of the circuit is properly operating, but in another part of the circuit, let's say you connect 10 of these, right? I mean, 10 gates, this one, this one, this one, right? So this will be creating some delays, and then the extra delay here is going to be critical. So that that's called the critical path, okay? Critical path determines the maximum operation frequency. Maybe for 99.9% of the circuit, there's no problem of these delays, cannot create a problem. But if one point, you know, creates a problem, then you should determine the maximum operation frequency according to that, the slowest node of the circuit. But right now we are doing, you know, individual definitions, and then we'll be doing one gate at a time, and then we'll be analyzing one gate, for example, okay? Is that clear? So instead of giving a break, I will continue and finish these definitions, and then maybe we can stop there for this week. Any other question? Okay, another important thing is the power dissipation. And the power dissipation is also important for each gate. Let's say you design a circuit and then it dissipates a lot of power, then it's not good, because then it will be limiting how many gates you can put into that circuit. Otherwise, it will be heating up too much. Okay, so therefore, what we do is we look at the power dissipation of each gate and each topology. So here, power dissipation, as you know, is going to be for this case like this. So, you know, we can look at the average power dissipation like this. How much power is dissipated from average power dissipation from VDD, and how much average power dissipation from PSS. Okay, so what do I mean? I mean, for this one, PDD average is calculated from this VDD times IDD when output is high plus IDD when output is low divided by 2. Okay, so when output is high and when output is low, I mean, we have seen in that example for output high case, the power dissipation was 0. So this was 0, but there was a power dissipation for this one. Okay. So this is drawn maybe wrong. I mean, I should just say plus here. And then also saying plus. According to this definition, it should be minus in there because of VSS. But if VSS is minus, it's also minus. Let me do this here also. Okay. PSS average is supply voltage and the current out of the supply voltage. Okay. So if the circuit was like this, let's say this is 5 volts and the current is 1 milliamp. And then here it's going to be 1 milliamp. And let's say this is minus 2 volts. Okay, what is the power dissipation here? Hmm? 5 volt times 1 milliamp plus minus 2 volts times the current out of the supply, which is 1 milliamp, minus 1 milliamp. So therefore, power dissipation is going to be 7 watts. Is that okay?
Olması gerekmiyor mu hocam?
Hmm?
Miliwatt olması gerekmiyor mu hocam?
Milliwatt. Yes, you're right. Thank you. Okay. So typically, you know, in order to reduce this delay, we need to charge the capacitances much faster. In order to charge the capacitances much faster, we need to maybe increase the current by reducing the resistances. But if we do that, then power dissipation will increase. Okay, so therefore, average power times average delay is called a parameter to consider power delay product. So if you increase the power dissipation, you can reduce the delay. But typically, you know, for a technology, this power delay product becomes fixed. So I mean, it's not so good to change the resistance values to increase the or decrease the power dissipation, because then delay is going to be increasing. So typically, in order to compare different technologies, we compare them not only by delay, not only by power, but by the multiplication of those two. And then if the power delay product is lower, then we say, oh, this technology is better compared to other technology. Okay. Or when I say technology, topologies. Okay. So we'll be seeing different logic gates, logic families. So when we want to compare them in terms of, you know, performance, it is better to look at power delay product instead of just looking at the delay or power dissipation. Is that okay? So in the coming hours, we will see how we can make an inverter, for example, or NAND gate, NOR gate, with these technologies. Like we already mentioned about RTL to you, so that you can understand, the idea here. But we will be looking at diode transistor logic, transistor logic, and then MOS-based logic families. And today, the dominant one is this one. This is the best one, CMOS. And we'll be seeing that, how we can implement that with the MOS technology. Is that okay? I can continue or give a break and continue or stop here. What do you say?
I think that's enough for today.
That's enough for today, okay. Definitions, you learn the definitions, you need to observe the definitions, okay. This is fine. So the diode logic is the worst one, and then it doesn't really practically work. But still, it's worth mentioning, like how we can make a logic circuit using a diode. Okay, we'll do that next Monday. Okay, so we'll be seeing this one by one, and now you will be understanding those definitions much better. Okay, thank you then.
Thank you hocam. See you later.
Thank you hocam.
Teşekkürler
See you
hocam.
later.
İyi günler hocam.
İyi günler hocam.
İyi günler hocam.
İyi günler hocam. İyi günler hocam.
Hadi görüşmek üzere. Evet.